Hello everyone. Welcome to Ancient Cosmos Sleep. Tonight, we drift into one of the oldest and most bewildering questions ever asked beneath a sky full of stars. How did the universe come into existence from nothing? You float in imagination above a dark and silent expanse. No galaxies swirl below you. No planets circle distant suns. No comets leave silver trails across the void. There is only a vast absence stretching in every direction, so empty that even the concept of distance feels unemployed. If this scene were completely accurate, you probably won't survive this. Then again, with no atoms, no time, and no space, there is technically nothing available to do the surviving. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're here, feel free to post your location and local time. It is always fascinating to see where in the world fellow travelers are listening from, as we wander through impossible questions together. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin with a question so simple that it almost sounds childish. Why is there something instead of nothing? Human beings have asked versions of this question for thousands of years. Ancient philosophers stared into the night and wondered where everything came from. Long before telescopes, before observatories, before anyone knew that our galaxy was merely one among billions, people tried to imagine a beginning. One mainstream historical fact is that the ancient Greek philosopher Parmenides argued more than 2,000 years ago that nothing could come from nothing. To him, existence itself seemed unavoidable. If something exists now, he reasoned, then existence must somehow always have been present in some form. As you sit with that thought, it feels strangely comforting and slightly annoying at the same time. After all, if existence has always existed, the mystery remains. You are still left staring into the darkness asking why. The trouble begins when you try to imagine nothingness itself. Your brain immediately cheats. You picture a black empty room, but a room is something. You picture empty space. Space is something too. You imagine a silent void. Silence still requires a place where sound could exist. Again and again, your imagination sneaks something into the picture. It turns out that true nothingness is surprisingly difficult to imagine. The human mind evolved to throw rocks, find food, remember faces, and occasionally panic over emails. It did not evolve to visualize the complete absence of reality. That may be why the question has survived for so long. Every answer seems to open another door. Suppose you somehow erase every star from the sky, then every galaxy, then every atom, then every particle, then even space itself. What remains? The answer sounds obvious. Nothing. Yet the moment you say the word, problems appear. Can nothing have properties? Can it be stable? Can it even exist? The sentence, "nothing exists," starts sounding suspiciously self-contradictory after a while, like a snake attempting to swallow a philosophy textbook. As centuries passed, thinkers continued wrestling with these puzzles. Some imagined eternal matter. Others proposed divine creation. Others argued that the question itself might be flawed. Even today, scholars and scientists continue debating what qualifies as a true explanation. Historians still argue whether certain ancient creation stories should be viewed primarily as religious accounts, philosophical speculation, or early attempts to understand natural processes. The line between those categories is not always as clear as modern readers assume. Meanwhile, the night sky above humanity remained largely mysterious. For most of history, people thought the stars were relatively nearby. They did not know that many visible stars sit dozens, hundreds, or even thousands of light years away. They certainly did not know that the Milky Way contains hundreds of billions of stars. Nor did they know that beyond it lie countless other galaxies scattered across unimaginable distances. You do. And that knowledge changes the emotional weight of the question. Because when you ask where everything came from, you are no longer asking about a village, a kingdom, or even a planet. You are asking about everything, every mountain, every ocean, every grain of sand, every whale song, every dinosaur footprint, every awkward family photograph, every black hole, every photon crossing the darkness, all of it. One quirky historical tidbit is that some ancient cultures imagined creation emerging from a cosmic egg. Versions of this idea appeared in different places around the world. The image is strangely charming. The entire universe waiting inside a giant celestial breakfast item. Compared with modern cosmology, it sounds fantastical, yet there is something familiar about it. An enormous reality emerging from a compact beginning. Human imagination often circles back to similar patterns. As the centuries rolled on, science gradually replaced speculation with observation. Telescopes improved. Measurements became more precise. Mathematics grew more powerful. The universe began revealing secrets that earlier generations could scarcely imagine. And one by one, old assumptions started falling away. The Earth was not the center of everything. The Sun was not unique. The Milky Way was not the entire cosmos. Each discovery made humanity seem smaller. Yet each discovery also expanded the scale of the mystery. By the early 20th century, scientists would uncover evidence that the universe itself is changing, not static, not frozen, not eternal in the way many had assumed. That realization would eventually point investigators toward an astonishing possibility. The universe may have had a beginning, for now, though you remain suspended in the darkness before that revelation arrives. You drift quietly through the question itself, not rushing toward answers, not demanding certainty, just noticing how extraordinary it is that reality exists at all. The pillow beneath your head exists. The air around you exists. The stars beyond the ceiling exist. Somehow, against all apparent odds, there is a universe here, rather than a perfect absence. And as your thoughts wander through that realization, you feel the scale of the puzzle expanding gently around you like a calm ocean at night. You do not need to solve it yet. You only need to follow it. The journey has barely begun, and already the mystery feels larger than galaxies. Soon you will start rewinding cosmic history itself, peeling back the layers of time and tracing everything you know toward a moment when the universe looked unimaginably different from the one surrounding you tonight. You continue drifting with the question hanging quietly above you, like a lantern suspended in a dark cosmic sea. Why is there something instead of nothing? The more closely you examine it, the stranger it becomes. The difficulty is not merely finding an answer. The difficulty is understanding the question itself, because before you can ask how the universe emerged from nothing, you must decide what nothing actually means. That sounds straightforward at first. It is not. Imagine someone hands you an empty glass. You look inside there, or also say, yet the glass contains air. Remove the air. Now the glass contains a vacuum. Surely that is nothing, except a vacuum still occupies space. It still has dimensions. It still follows physical laws. You have removed matter, but you have not removed reality. The word nothing keeps slipping away like a bar of soap dropped in a bathtub. Philosophers have spent centuries wrestling with this problem. One mainstream historical fact is that the German philosopher Gottfried Wilhelm Leibniz famously framed the question, why is there something rather than nothing, during the 17th century. His version became one of the most influential formulations ever proposed. You can almost picture him staring thoughtfully into candlelight, unknowingly creating a puzzle that future generations would still be arguing about hundreds of years later. Not bad for a question. Most questions eventually receive answers. This one seems to collect more questions instead. As you examine the idea of nothingness, your mind naturally tries constructing images: a black void, an empty room, an endless darkness. Yet every image contains something. Darkness is still a condition. A void still occupies space. An empty room still requires walls. Even your imagination struggles to eliminate reality completely. It is a bit like trying to draw a picture of invisible ink using invisible ink. The tools themselves refuse to cooperate. Some philosophers argue that absolute nothingness is impossible. Not unlikely, not difficult, impossible. According to this view, existence may be more fundamental than non-existence. Reality simply is. You may not find that satisfying, many people do not. It can feel suspiciously, like answering a difficult question by shrugging politely. Yet the idea continues attracting serious attention. Others take a different approach. Perhaps nothingness is possible, but unstable. Maybe a state of complete emptiness cannot remain empty forever. Maybe reality naturally emerges from it. This possibility will become especially important once modern physics enters the story. For now, though, you are still exploring concepts rather than equations. Imagine stripping reality away, layer by layer. First, the stars vanish, then planets, then atoms, then light, then every particle. Eventually, even space disappears. No dimensions, no distances, no directions, no past, no future, nothing remains. At least that is what the description says. But notice how quickly language begins malfunctioning. If space does not exist, where is this nothing? If time does not exist, how long does it last? If absolutely nothing exists, can you even describe it? The moment you attempt to discuss nothingness, you accidentally start treating it like something, a location, a condition, a state. The grammar itself rebels. Words evolved inside reality. They were not designed for discussing the absence of reality. This creates a surprisingly serious challenge for cosmologists and philosophers alike. When someone says the universe came from nothing, the next question becomes unavoidable. What kind of nothing? Philosophical nothing? Physical nothing? Mathematical nothing? Each possibility means something different. A modern physicist might describe empty space as a vacuum, but a philosopher could immediately object. A vacuum contains physical laws. A vacuum contains structure. A vacuum is definitely not nothing. The debate can sometimes resemble two people arguing over whether a dragon is green while simultaneously disagreeing about the definition of dragon. Not surprisingly, misunderstandings occur. One quirky tidbit comes from ancient Chinese philosophy, where certain traditions discuss concepts resembling fertile emptiness rather than absolute non-existence. In some interpretations, the void was not a barren absence but a source from which forms could emerge. The imagery is beautiful, an emptiness that is somehow creative, a silence that contains potential, a blank page already hinting at future stories. Across cultures, humans repeatedly stumbled towards similar intuitions. Perhaps emptiness and possibility are not opposites. Perhaps they are closely connected. Yet modern science approaches these questions differently. Science relies upon observation and measurement. It seeks explanations that can be tested. And this creates a dilemma. How do you test nothing? You cannot put absolute non-existence inside a laboratory. You cannot measure it with instruments. You cannot collect samples of it. No funding agency has ever approved a grant proposal titled Weekend Expedition into Total Non-Existence. At least not successfully. As a result, scientists often focus on questions they can investigate directly. What was the early universe like? How did matter form? How did galaxies emerge? These questions leave traces that can be observed. Nothingness does not, or so it seems. The story becomes even more intriguing when 20th century physics begins revealing that empty space is not truly empty. At first, this sounds like a technical detail. Later, it will become one of the most important clues in the entire mystery. For now, though, you remain in the conceptual wilderness where definitions matter enormously. Historians still argue whether certain philosophical traditions anticipated aspects of modern cosmological thinking, or whether similarities are mostly coincidental. The comparisons remain fascinating but controversial, and controversy thrives wherever ultimate origins are discussed. perhaps that is unavoidable. After all, you are probing the edge of human understanding. You are asking questions that touch the foundations of existence itself. Questions that challenge intuition. Questions that expose the limitations of language. Questions that make ordinary reality suddenly feel extraordinary. The ceiling above you, the floor beneath you, the distant stars, the atoms inside your body, all of them participate in a reality that did not have to exist, or perhaps could not help existing. You do not know yet, neither does anyone else with complete certainty. That uncertainty is not a failure. It is part of the adventure, as the darkness around you remains calm and silent. You begin preparing for a different kind of journey. The philosophical puzzles remain important, but soon you will start examining evidence, observations, measurements, clues scattered across the cosmos itself. The universe has left behind a trail of breadcrumbs stretching billions of years into the past, and if you follow that trail carefully enough, you can begin rewinding cosmic history. Galaxies will shrink, distances will collapse, time itself will seem to flow backward. The vast universe surrounding you tonight will gradually become smaller, hotter, denser, and stranger. And somewhere along that path, the question of origins will take on an entirely new shape, not because the mystery disappears, but because, for the first time, you will be able to watch the universe retrace its own steps toward the beginning. You begin the rewind slowly, not because the universe resists, but because your imagination needs a moment to adjust. Everything around you appears familiar at first. Galaxies drift through enormous stretches of space. Stars shine steadily. Planets circle their suns. Somewhere, people are making coffee, misplacing their keys, and confidently clicking "Remind me tomorrow" on software updates they have already postponed for 6 months. Reality feels comfortably established, ancient, permanent, yet appearances can be deceptive. You start turning the cosmic clock backward. A few centuries pass, then thousands of years, then millions. Nothing dramatic happens at first. The stars continue shining. The constellations slowly rearrange themselves. Continents shift across Earth's surface. Mountains rise and erode. Life evolves. The universe remains recognizable, but as the rewind accelerates, larger changes emerge. Dinosaurs return, then disappear into deeper time. Flowering plants vanish. Mammals shrink into tiny nocturnal creatures. The oceans transform. Entire ecosystems come and go. You continue moving backward. Hundreds of millions of years pass like drifting clouds. The Earth itself changes beyond recognition. Eventually, the planet becomes molten. Its surface glows red-hot beneath a violent young sun. Continue farther. The moon drifts closer. The atmosphere transforms. The oceans disappear. The Earth itself finally dissolves into the swirling material from which it formed. The familiar world is gone, yet the universe remains. Stars still shine. Galaxies still spin. The great cosmic structures endure. For now, you continue rewinding. Billions of years slip past. Galaxies grow younger. Collisions that have not yet happened suddenly reverse themselves. Stars that once died return to life. Black holes shrink as matter emerges from them. The entire cosmos begins looking increasingly crowded. One mainstream historical fact is that in 1929, the astronomer Edwin Hubble published observations showing that distant galaxies are moving away from us. The farther away a galaxy is, the faster it generally appears to recede. This discovery changed everything. Before then, many scientists assumed the universe was static and eternal, a cosmos that neither expanded nor contracted, a cosmic backdrop that simply existed. Hubble's observations suggested something radically different. The universe was expanding. Space itself was stretching. You can picture it like dots drawn on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot. No single dot sits at the center. The expansion occurs everywhere at once. The analogy is imperfect, but it captures the basic idea. And now, as you continue rewinding the cosmic film, That expansion runs backward. Galaxies move closer together, clusters compress, distances shrink, the entire observable universe becomes denser, hotter, more crowded. At first, this realization seems straightforward. If the universe is expanding today, then it must have been smaller yesterday, smaller still before that, and smaller before that. Keep tracing the process backward far enough, and eventually everything appears to converge toward an incredibly compact state. This insight gave rise to what later became known as the Big Bang theory. Ironically, the phrase Big Bang was originally coined by astronomer Fred Hoyle during a radio broadcast, partly as a criticism of the idea. Yet the nickname stuck so effectively that almost everyone uses it today. History occasionally has a sense of humor. Imagine spending years criticizing a theory only to accidentally provide its permanent branding. That is the scientific equivalent of inventing a rival restaurant's slogan. As the rewind continues, galaxies themselves begin disappearing, not because they cease to exist, but because they have not formed yet. Stars vanish, planets vanish, heavy elements vanish. The familiar ingredients of reality are gradually stripped away. You move deeper into the past. The universe becomes increasingly simple. Hydrogen dominates. Then even atoms begin struggling to survive. Temperatures climb relentlessly. Matter and radiation mingle in a brilliant, opaque sea. The cosmos starts resembling a furnace more than a collection of celestial objects. If you could somehow witness it directly, it would not look like an explosion occurring in space. This is one of the most common misconceptions. The Big Bang was not an explosion inside pre-existing emptiness. Space itself participated in the expansion. The universe was not expanding into something else. Rather, the distances between regions of space were increasing. This distinction sounds subtle. It is actually profound because it means there may not have been an outside for the universe to expand into. No surrounding void, no giant cosmic room, just reality itself changing. You continue backward. Millions of years become thousands, thousands become centuries, centuries become days, days become seconds. The universe now glows with incredible intensity. Radiation dominates everything. Particles collide constantly. The conditions become so extreme that ordinary experience offers almost no useful comparison. Even the core of the sun seems modest by comparison. A quirky cosmological tidbit, occasionally mentioned in popular science, is that if the entire observable universe could somehow be compressed into an extraordinarily tiny volume, its density would be almost impossible for the human mind to grasp. Numbers become so large that they stop feeling meaningful and start feeling decorative. You know the sensation. Someone says a trillion, trillion, trillion. Your brain politely nods and then quietly leaves the meeting. Yet these unimaginable scales are exactly what cosmologists must confront. The further backward you travel, the stranger reality becomes. Physical conditions approach extremes never reproduced in laboratories. Matter behaves differently. Energy dominates. Known physics begins stretching toward its limits. Still, the evidence supporting an early hot, dense universe, remarkable by strong. Astronomers observe galaxies receding. They detect the cosmic microwave background radiation, a faint glow left over from the early universe. They measure the abundance of light elements formed during the cosmos's first minutes. Together, these clues paint a remarkably consistent picture. A universe that evolved, a universe with a history, a universe that was once vastly different from the one surrounding you tonight. Historians still argue whether the public initially understood the implications of cosmic expansion, as quickly as later accounts sometimes suggest. Revolutionary ideas often spread more gradually than legends imply. And revolutionary this idea certainly was. For centuries, many people imagined the cosmos as eternal and unchanging. Now evidence suggested a dynamic universe with a past, a universe whose history could be reconstructed, a universe that seemed to point toward a beginning, Yet as you approach those earliest moments, confidence begins to weaken. The equations remain powerful, but eventually they lead into territory where known physics becomes incomplete. The closer you get to time zero, the less certain the map becomes. It is like following a trail through a forest until the path suddenly vanishes into fog. You can see where you have been. You can estimate where the trail continues. But certainty fades. Ahead lies an error so extreme that gravity, quantum mechanics, space, and time themselves may behave in unfamiliar ways. The rewind continues. The universe shrinks further, temperatures soar higher, and somewhere just ahead waits the first tiny instant, a realm where the laws of physics begin whispering that they no longer have the full story. The rewind carries you farther still. Galaxies are gone, stars are gone, atoms are gone. Even the familiar particles that make up ordinary matter exist only as fleeting participants in a blazing cosmic storm. The universe has become almost unimaginably small, hot, and dense. Yet despite all the strangeness, the laws of physics continue guiding your journey backward, at least for a while. The closer you approach the beginning, the more extreme everything becomes. Temperatures climb beyond anything found inside stars. Energy densities soar. The distinction between matter and radiation starts losing much of its everyday meaning. Reality itself begins looking less like a collection of objects and more like a restless ocean of pure energy. You continue drifting backward through fractions of seconds, not milliseconds, not microseconds, much smaller intervals than those. Tiny slices of time so brief that ordinary language struggles to describe them. A nanosecond suddenly seems leisurely. A trillionth of a second starts feeling almost generous. And still you continue. Eventually you arrive at a boundary known as the Planck time. This interval is extraordinarily small, unsurpassed 39 times 10^44 text seconds. That number is difficult to appreciate. Light, the fastest thing known, would travel only an incredibly tiny distance during such an interval. The Planck time represents a region where our current understanding of physics features a profound limitation. One mainstream historical fact is that the concept is named after Max Planck, whose work at the beginning of the 20th century helped launch quantum theory and transformed modern physics. His ideas would eventually influence nearly every attempt to understand the universe's earliest moments. As you approach the Planck era, something unusual happens. The equations that describe gravity begin colliding with the equations that describe quantum mechanics. Both theories are extraordinarily successful. Quantum mechanics explains the microscopic world with astonishing precision. Einstein's theory of general relativity describes gravity, stars, black holes, and cosmic expansion with equal brilliance. The problem is that the two frameworks do not fit together comfortably under the extreme conditions of the very early universe. Most of the time this mismatch is not noticeable. Planets orbit happily. Atoms behave properly. Physicists go about their work. The cosmic machinery functions. But at sufficiently high energies and tiny scales, the disagreement becomes impossible to ignore. Imagine owning two maps. One perfectly describes every road in Europe. The other perfectly describes every road in Asia. Both are accurate. Yet when you try connecting them along a particular border, the roads suddenly stop matching. That does not mean either map is useless. It means something important is missing. The earliest universe appears to sit directly on that missing border. Gravity becomes enormously strong. Quantum effects become unavoidable. And our best theories begin speaking different mathematical languages. This is why cosmologists often say they lack a complete theory of quantum gravity. They possess remarkable pieces of the puzzle. The final picture remains unfinished. As you hover near the Planck era, certainty starts fading into speculation. Observations can guide you only so far. Beyond that point, theory must carry much of the burden. The universe becomes a place where space and time themselves may behave very differently from anything familiar. Some researchers suspect space is not infinitely smooth. Perhaps it possesses an underlying quantum structure. Perhaps spacetime resembles a kind of microscopic foam, tiny fluctuations bubbling constantly at scales far smaller than anything directly observed. The image is strangely poetic, reality appearing solid from a distance yet becoming frothy and restless upon closer inspection, like an ocean viewed from orbit, smooth from afar, wildly complex up close. One quirky tidbit sometimes discussed in theoretical physics is the idea that at sufficiently tiny scales, the geometry of space-time might fluctuate so violently that concepts like distance become difficult to define consistently. The universe itself would resemble a landscape that cannot decide on its own shape. You can imagine trying to measure the length of a coastline while the coastline continuously changes beneath your feet. Not an ideal surveying situation. Even the most patient cosmic cartographer might request a transfer. As you continue exploring this mysterious era, you discover that the very concept of a beginning becomes less straightforward. Many people imagine the Big Bang as a singular point where everything suddenly appears. Popular illustrations often show an infinitely dense dot erupting into existence. Reality may be considerably more subtle. The mathematical singularity that appears in certain equations often signals that the theory itself has reached its limits. A singularity may indicate not a physical object, but an incomplete description. Think of it as a warning label. The equations are saying, proceed carefully. Beyond this point, additional physics required. That distinction matters enormously, because if the singularity marks the breakdown of current theories, then asking what happened before it may still be meaningful. Not necessarily answerable, but meaningful. This possibility has inspired decades of research. Scientists have proposed many different approaches: string theory, loop quantum gravity, emergent spacetime models, various quantum cosmological frameworks. Each attempts, in its own way, to extend understanding beyond the edge of known physics. None has yet achieved universal acceptance. Historians still argue whether future generations will view today's competing theories as major breakthroughs or merely stepping stones towards something entirely different. Scientific revolutions often look obvious after they happen. While standing inside them, uncertainty dominates. That uncertainty surrounds you now. The universe has become so young that familiar concepts barely apply. There are no galaxies, no stars, no planets, no chemistry, no biology, not even stable particles in the ordinary sense. Only a realm of extraordinary energy and profound mystery. Yet despite the uncertainty, researchers remain remarkably confident about one thing. The universe evolved from an extremely hot, dense early state. The evidence supporting that conclusion is powerful. The details of the earliest fractions of a second remain the great challenge. And somewhere just beyond the Planck era lies one of the most remarkable ideas in modern cosmology. An event so dramatic that it may have reshaped the entire cosmos in an instant. A period during which the universe expanded at an almost unimaginable rate. A growth so rapid that even the word explosion feels inadequate. As the darkness around you shimmers with the energy of a newborn cosmos, you drift toward that astonishing possibility. The universe is about to undergo a transformation so extreme that it will determine the structure of galaxies billions of years later. A fleeting moment, an immense consequence. And the first hints of it are already beginning to emerge from the quantum haze. The quantum haze begins to thin. Not completely. The earliest universe remains wrapped in mystery. Yet, as you drift forward through the first fractions of a second, a remarkable idea starts taking shape. An idea so bold that when it was first proposed, many physicists regarded it with a mixture of fascination, skepticism, and the academic equivalent of slowly raising one eyebrow. The universe, according to this proposal, may have experienced a brief episode of extraordinarily rapid expansion. not merely fast, not astonishingly fast, unimaginably fast. This event is known as cosmic inflation. One mainstream historic fact is that the inflationary model was first developed in the early 1980s by physicist Alan Guth, who sought to explain several puzzling features of the observable universe. His proposal would eventually become one of the most influential ideas in modern cosmology. To appreciate why inflation matters, you first need to notice something peculiar about the universe around you. Look in one direction, then another, then another. On the largest scales, the cosmos appears remarkably uniform. The temperature of the cosmic microwave background, the faint afterglow of the early universe, is nearly identical across enormous regions of the sky. That sounds ordinary at first, but it creates a puzzle. Those distant regions are so far apart that, according to simple Big Bang expansion alone, they should never have had time to communicate with one another. Imagine finding two strangers on opposite sides of Earth, wearing perfectly matching outfits, speaking identical sentences, and somehow humming the same tune. You would naturally suspect some prior connection. The universe presents a similar mystery. How did distant regions become so similar? Inflation offers an answer, according to the theory. Before the observable universe expanded into its present size, it occupied a much smaller region. A region compact enough for different parts to interact and reach similar conditions. Then something extraordinary happened. The universe expanded at a tremendous rate, not because galaxies flew apart. Galaxies did not yet exist, space itself stretched. You can picture a tiny patch of reality suddenly swelling enormous proportions. Small irregularities became spread across vast distances. Previously connected regions became separated by unimaginable expanses. The result was the large-scale uniformity astronomers observe today. The numbers involved are difficult to comprehend. During inflation, the universe may have expanded by an enormous factor within an extraordinarily tiny fraction of a second, a propto, EHT. This simple mathematical relationship describes exponential growth, where expansion accelerates dramatically over time. The equation looks calm and innocent. Its consequences are anything but. Exponential growth has a talent for producing absurd results. Ask anyone who has forgotten to cancel a free trial subscription. The universe, however, operated on a rather larger scale. As inflation unfolded, space expanded faster than light could cross the growing distances. This statement sometimes sounds alarming. Fortunately, it does not violate Einstein's theory of relativity. Objects moving through space remain limited by the speed of light, but space itself can expand in ways that increase separation distances much more rapidly. The distinction is subtle but important, and during inflation, that distinction became everything. You drift through this strange era. The universe is still incredibly young, still unimaginably hot. Yet inflation transforms its geometry. Any initial curvature becomes stretched flatter. Tiny irregularities become diluted. The cosmos emerges smoother and more uniform than it otherwise would have been. It is rather like taking a wrinkled sheet and pulling it tight across an enormous frame. The wrinkles do not necessarily disappear completely, but they become much less noticeable. And those remaining wrinkles turn out to be crucial. Because inflation does not create perfect smoothness, quantum physics refuses to allow that even during inflation, microscopic fluctuations continue occurring. Tiny variations, minuscule differences in energy density, small enough to seem insignificant, yet the future of every galaxy depends on them. One quirky tidbit about inflation is that some physicists jokingly describe the early universe as the most successful growth startup in cosmic history. It expanded from something extraordinarily tiny into something vastly larger before most of reality had time to notice what was happening. Unlike modern startups, however, inflation appears to have delivered on at least some of its promises. The evidence supporting it has grown steadily over decades. Measurements of the cosmic microwave background reveal patterns remarkably consistent with predictions derived from inflationary models. Observations continue testing the theory in increasingly sophisticated ways. Yet important questions remain. What exactly caused inflation? What field or mechanism drove it? How did it begin? How did it end? Researchers possess candidate explanations. No definitive answer has emerged. As often happens in science, solving one mystery uncovers several more waiting behind it. The universe remains generous with puzzles. Historians still argue whether inflation will ultimately be remembered as one of the greatest scientific insights ever developed, or whether future theories will substantially modify its current form. The debate remains active and healthy. Scientific ideas grow stronger when challenged. As inflation continues unfolding around you, another remarkable consequence appears. Those tiny quantum fluctuations present during this era become stretched to cosmic scales. Microscopic variations are enlarged enormously. The smallest irregularities become the seeds of future structure. Billions of years later, gravity will amplify those slight differences. Regions with marginally greater density will attract more matter. Clouds will form, stars will ignite, galaxies will emerge, clusters of galaxies will assemble. Everything you see in the modern cosmos traces part of its ancestry back to those tiny fluctuations. The stars above your head tonight, the Milky Way itself, the atoms inside your body, all connected, in a distant sense, to subtle quantum variations present during the universe's earliest moments. That realization feels almost impossible to grasp. A microscopic fluctuation influencing the formation of galaxies billions of years later, yet nature routinely performs feats that sound improbable before becoming familiar. As inflation eventually ends, enormous energy becomes converted into particles and radiation. The universe fills with matter. The stage is set for the hot Big Bang evolution that follows. The cosmos begins taking on a form that increasingly resembles the one scientists can reconstruct through observation. Still, an important clue lingers behind. Inflation appears to connect the largest structures in existence with the smallest processes known to physics. Galaxies may owe their existence to quantum events. The vast may emerge from the tiny. The cosmic may originate in the microscopic. And that connection points directly toward an even stranger possibility. Because if quantum fluctuations helped shape the universe, perhaps quantum processes played an even deeper role. Perhaps they reach all the way back toward the question that started this journey. The question of something and nothing, the question of origins, the question of whether emptiness itself might possess hidden activity. Ahead lies a realm where the vacuum is not truly empty, where particles flicker briefly into existence, and where reality becomes far more restless than the word nothing ever suggests. The darkness waits patiently. And within that darkness, quantum fireflies are already beginning to appear. The darkness no longer looks empty, at least not to modern physics. You drift into a realm where one of the most surprising discoveries of the 20th century begins reshaping your understanding of reality. The empty vacuum that once seemed like the perfect candidate for nothing turns out to be far more complicated. In fact, it may be busy, very busy. Not busy in the way a city street is busy. Not busy in the way your email inbox becomes busy the moment you finally decide to relax. Bussy in a deeper and stranger sense. According to quantum theory, what appears empty may actually contain continual activity occurring beneath the threshold of ordinary observation. The vacuum, it seems, is restless. To understand why, imagine shrinking yourself to scales far smaller than atoms, smaller than atomic nuclei, smaller still. As you descend into the quantum world, certainty begins dissolving. Objects stop behaving like tiny billiard balls. Particles exhibit wave-like properties. Probabilities replace simple predictability. Reality becomes less like a machine and more like a cloud of possibilities. One mainstream historical fact is that the development of quantum mechanics during the early 20th century involved contributions from physicists such as Werner Heisenberg, Erwin Schrödinger, and Niels Bohr, whose work transformed humanity's understanding of nature at its morseless scales. The results were astonishing and occasionally headache-inducing. Even many of the scientists involved spent years debating what quantum theory actually meant. You can sympathize, the theory works extraordinarily well, yet its implications often feel deeply counterintuitive. Among its most famous features is the uncertainty principle. In simplified terms, certain pairs of physical quantities cannot both be known with perfect precision simultaneously. The universe places limits on certainty itself. That may sound philosophical. It is actually embedded within the mathematics. One consequence is that quantum fields cannot remain perfectly still. Even the vacuum retains subtle fluctuations, tiny variations, microscopic jitters, permanent background activity. You can think of a calm ocean. From high above, the surface appears smooth. Approach more closely and countless ripples become visible. Volume in further, and additional patterns emerge. The vacuum behaves somewhat similarly. What appears empty from a distance reveals structure when examined more carefully. This leads to one of the most famous concepts in popular descriptions of quantum physics: virtual particles. These are often described as particle-antiparticle pairs briefly appearing and disappearing within the vacuum. The imagery is memorable: particles flickering into existence like fireflies on a summer night, then vanishing almost immediately. The picture is simplified, but it captures an important intuition. The vacuum is not an inert emptiness. It possesses quantum activity. It seethes with fluctuations. It vibrates with possibility. A quirky tidbit often mentioned in physics discussions is that if empty space were truly empty in the classical sense, many observed phenomena would be difficult to explain. Experiments reveal measurable effects associated with quantum vacuum behavior, meaning that nothing behaves suspiciously like something. The vacuum has become the most overqualified version of nothingness ever proposed. Imagine applying for a job and describing yourself as empty, while simultaneously containing quantum fields, fluctuating energies, and measurable physical properties. Your resume would raise questions. Yet nature seems comfortable with the arrangement. As you continue drifting through this quantum landscape, another realization appears. The vacuum is not merely a background. Quantum fields permeate reality. Particles arise as excitations within these fields. In a sense, the fields themselves are fundamental. The vacuum represents their lowest energy state, but lowest energy does not mean zero activity. That distinction is crucial, because when physicists discuss a quantum vacuum, they are not describing philosophical nothingness. They are describing a physical state governed by laws, fields, and mathematical structure. This difference often causes confusion in public discussions. When someone claims that the universe could arise from nothing, critics frequently respond that a quantum vacuum is obviously not nothing. And they have a point. The vacuum contains quite a lot: fields, rules, potential, structure. The debate partly becomes a disagreement over definitions. You may recall the difficulties encountered earlier when trying to define nothingness. Those difficulties have not disappeared. They have simply followed you into modern physics. Historians still argue whether popular presentations of quantum cosmology sometimes blur the distinction between philosophical nothingness and physical vacuum states more than specialists would prefer. The tension remains active today, yet regardless of terminology, the quantum vacuum introduces an extraordinary possibility. If empty space contains fluctuations, then perhaps creation is not as simple as once imagined. Perhaps reality possesses a built-in tendency toward activity. Perhaps apparent emptiness hides latent potential. To appreciate how radical this idea is, imagine an absolutely calm pond. Then imagine tiny ripples continually emerging without any obvious disturbance. The pond never remains perfectly still. The vacuum behaves somewhat like that. Quantum fluctuations occur naturally, not because something externally triggers them, because the laws of quantum physics permit them. As the early universe evolves, these fluctuations become increasingly important. Remember the inflationary era. Tiny quantum variations were stretched to enormous scales. Those microscopic differences eventually helped seed galaxies and cosmic structure. In other words, the largest objects in the universe may trace part of their origin to fluctuations occurring within the quantum vacuum, a remarkable connection, the very small influencing the unimaginably large. And now your thoughts naturally return to the question that launched this journey. If quantum fluctuations can create particles temporarily, could something similar occur on a far grander scale? Could an entire universe emerge through related processes? The possibility sounds outrageous. Then again, many ideas in modern cosmology sound outrageous until the equations arrive. Nature rarely consults human intuition before deciding how to operate. The vacuum itself already behaves in ways that would have seemed absurd to earlier generations. Invisible fields, temporary particles, energy fluctuations, all hidden beneath ordinary experience, reality continues proving more inventive than common sense. As you float through this quantum darkness, the fireflies continue appearing and disappearing. Tiny flashes, brief possibilities, momentary patterns emerging from the vacuum. Most vanish almost instantly, they leave no lasting mark, yet their existence demonstrates something profound. Emptiness is not necessarily silent. Nothingness, at least in the physical sense explored by quantum theory, may contain far more activity than its name suggests. And if the vacuum possesses such restless energy, a tantalizing question begins forming at the edge of your thoughts. What if a fluctuation did not disappear? What if a quantum event grew rather than faded? What if one tiny possibility expanded into something vastly larger? Perhaps even large enough to become a universe. The idea remains speculative, the evidence incomplete, the debate ongoing, yet it stands among the most fascinating proposals ever developed in humanity's attempt to understand cosmic origins. Ahead lies the possibility that something could emerge naturally from processes woven into the fabric of reality itself. And the closer you examine that possibility, the more surprising the universe becomes. The quantum fireflies continue flickering around you. Tiny fluctuations emerge, tiny fluctuations vanish. The vacuum remains restless, never settling into the perfectly silent nothingness that earlier generations once imagined. And now a bold possibility begins to take shape. What if a fluctuation did not simply disappear? What if, under the right conditions, a tiny quantum event expanded rather than faded? What if an entire universe could emerge from processes built into the fabric of reality itself? You immediately sense why this idea attracts attention. It seems to offer a possible answer to one of the oldest questions ever asked. How could something arise from nothing? Or at least from something that appears very close to nothing? The distinction matters, because as you discovered earlier, physicists and philosophers often mean different things when they use the word nothing. A quantum vacuum contains laws, fields, and structure. Philosophical nothingness contains none of these. The difference remains one of the central points of debate. Still, modern cosmology has produced several fascinating proposals suggesting that universes might emerge naturally from quantum processes. One mainstream historical fact is that physicist Alexander Vilenkin developed influential models exploring how a universe might quantum mechanically into existence under certain conditions. His work became part of a broader effort to understand cosmic origins using quantum theory. The phrase quantum tunneling sounds technical. The underlying idea is wonderfully strange. In everyday life, barriers tend to behave like barriers. If a ball lacks sufficient energy, It cannot roll through a solid wall, civil, predictable, comforting. Quantum particles, however, occasionally ignore this expectation. Under certain circumstances, they can appear on the opposite side of barriers that classical physics would forbid them from crossing. Not because they smash through, not because they tunnel with tiny quantum shovels. The mathematics simply allows a probability that the particle may be found beyond the barrier. Quantum reality plays by rules that often feel less like common sense and more like a very confident magician refusing to explain the trick. Some cosmologists wondered whether similar principles might apply to the universe itself. Perhaps reality could transition from one state to another through quantum processes. Perhaps a universe could emerge from an extremely simple initial condition. Perhaps existence does not require an external trigger in the way ordinary events seem to. The proposal remains speculative, yet it emerges naturally from attempts to combine cosmology and quantum mechanics. As you drift through these ideas, imagine a landscape of possibilities, not a physical landscape of mountains and rivers, a mathematical landscape. Different configurations of reality occupy different regions. Some are stable, some unstable, some capable of evolving into expanding universes. Within such frameworks, the birth of a cosmos may resemble a transition between states, a quantum event with enormous consequences. One quirky tidbit is that some popular science writers have compared universe creation to bubbles forming within a boiling liquid. The analogy is imperfect, but it provides an intuitive image, small regions emerging, growing, and developing their own properties. Unlike kitchen cookware, however, these cosmic bubbles involve significantly fewer recipe instructions and substantially more advanced mathematics, probably for the best. No one wants to discover that existence depends upon a forgotten ingredient. You continue floating through the conceptual landscape. The deeper you travel, the more you realize that modern cosmology often challenges assumptions inherited from everyday experience. Ordinary intuition evolved for survival on Earth's surface. It handles falling objects, moving animals, and suspicious noises in the dark reasonably well. It was not optimized for contemplating universe creation. As a result, many proposed explanations initially feel bizarre. Yet bizarre does not necessarily mean wrong. The universe has repeatedly demonstrated a willingness to behave in ways that seem counterintuitive. Earth orbits the sun, time slows under extreme conditions, space expands, black holes exist, quantum particles tunnel. Reality already contains plenty of surprises. Why should cosmic origins be simple? Some theories go even further. They suggest that universe creation may not be an exceptionally rare event. Perhaps new universes emerge repeatedly. Perhaps reality naturally generates them under certain conditions. Perhaps our cosmos is only one example among many. That possibility will become increasingly important later. For now, your attention remains focused on a narrower question. Can quantum physics explain how existence begins? The honest answer is that nobody knows for certain. Researchers have proposed intriguing models. Mathematics provides suggestive possibilities. Observations offer indirect clues. Definitive proof remains elusive. Historians still argue whether future generations will regard today's quantum creation scenarios as major breakthroughs or merely early approximations of a deeper theory not yet discovered. Scientific history contains many examples of ideas that were partly correct while still incomplete. The truth often arrives in stages, yet even uncertainty can be illuminating. The existence of serious scientific models exploring cosmic origins demonstrates something important. The question itself has moved beyond pure speculation. Scientists are attempting to formulate testable frameworks. They are building mathematical descriptions. They are asking how evidence might distinguish between competing possibilities. That shift matters enormously. You are no longer dealing solely with philosophical reflection. you are entering the realm of quantitative cosmology. Equations, predictions, optimal consequences. The mystery remains profound, but the tools have become more sophisticated. As your thoughts continue wandering, another intriguing realization emerges. Many creation scenarios rely upon an unexpected ingredient. Energy, not merely the presence of energy, its balance, its accounting, its distribution. Because if a universe emerges, an immediate question follows: where did all the energy come from? The stars contain energy. Matter contains energy. Radiation contains energy. Galaxies contain staggering quantities of it. The observable universe appears astonishingly rich. If all of that emerged naturally, some explanation seems necessary. This concern has motivated another influential line of thinking. Perhaps the total energy of the universe is not as large as it appears. Perhaps positive and negative contributions balance one another. Perhaps reality's accounting ledger works differently than intuition suggests. The idea sounds almost suspiciously convenient, yet many physicists take it seriously, and if correct, it could transform how you think about cosmic origins. The universe may contain enormous amounts of stuff, while still maintaining a surprisingly balanced overall budget. A cosmic bookkeeping trick hidden within the laws of physics. You continue drifting through the darkness. The quantum fireflies fade into the distance behind you. Ahead lies a new puzzle, not how a universe might begin, but how a universe containing everything could potentially cost almost nothing. And the answer, if there is one, may depend on understanding one of the strangest accounting systems ever imagined. The idea lingers in your thoughts. A universe containing hundreds of billions of galaxies, trillions upon trillions of stars, unimaginable quantities of matter and radiation, and yet somehow, perhaps, costing almost nothing. At first glance, the proposal sounds suspicious, like someone arriving at a luxury hotel, ordering every item on the menu, reserving the penthouse suite, and then calmly explaining that the total bill comes to exactly zero. You would probably request additional clarification. Fortunately, physicists have spent considerable time attempting to provide it. The key lies in energy, more specifically, in the possibility that different forms of energy may balance one another. One mainstream historical fact is that the famous relationship developed by Albert Einstein revealed that mass and energy are deeply connected, e.m.2. This transformed humanity's understanding of matter. Mass itself represents a form of stored energy. Every atom around you contains energy. Every star radiates energy. Every galaxy embodies immense quantities of it. Viewed this way, the universe appears extraordinarily wealthy. Yet gravity introduces an intriguing complication. In physics, gravitational energy is often treated as negative. That description can sound odd at first. After all, gravity feels very real. You drop an object. The floor confirms gravity's existence rather effectively. But when physicists calculate certain gravitational contributions, negative values naturally appear. Imagine lifting a ball away from Earth. You must invest energy to separate it from the planet's gravitational pull. The closer the ball remains to Earth, the lower its gravitational potential energy. The mathematics leads to a negative quantity relative to a chosen reference point. This seemingly technical detail becomes enormously important in cosmology because the universe contains not only positive forms of energy, but also gravitational effects that contribute negatively. And some researchers have suggested that the total may balance remarkably closely. Positive energy from matter and radiation, negative energy associated with gravity, together producing an overall sum near zero. The idea is astonishing. An entire universe emerging while preserving a kind of cosmic accounting balance, not free in every sense but balanced, like withdrawing and depositing identical amounts simultaneously. You drift through the concept slowly. The more you examine it, the more elegant it appears. A universe that can exist because its total ledger remains approximately neutral. a cosmos that does not violate conservation principles because the books balance from the beginning. Some cosmologists have found this possibility deeply appealing. It suggests that existence may not require an enormous initial energy investment. Reality could emerge while maintaining overall balance. One quirky tidbit, often repeated in popular science discussions, is that physicists sometimes joke about the universe being the ultimate free lunch. The phrase became associated with the notion that cosmic expansion and gravitational energy might allow a universe to arise without requiring a net positive energy budget. For once, the phrase free lunch comes with several pages of advanced mathematics attached. Nothing in cosmology is ever truly simple. As you continue contemplating the idea, it becomes clear that important caveats remain. Calculating the total energy of the universe is not always straightforward. Different cosmological models approach the issue differently. General relativity complicates matters considerably. Space itself evolves. Geometry changes. Global energy definitions become surprisingly subtle. This is not a situation where someone can casually add a few numbers on a napkin and announce victory. Many technical challenges remain, yet the broader insight persists. The universe may possess a natural mechanism for balancing positive and negative contributions. And if that is true, then the question of origins begins looking slightly different. Instead of asking where all the energy came from, you might ask whether the total was ever significantly positive to begin with. The shift is subtle. Its implications are profound. Historians still argue whether future developments in cosmology will strengthen the zero-energy universe concept or reveal important limitations in current interpretations. The debate remains active. As with many questions near the frontier of science, certainty is still under construction, yet even incomplete ideas can illuminate unexpected paths. The possibility of energy balance helps explain why some physicists feel comfortable discussing spontaneous universe creation. If a universe can emerge while preserving an overall energy balance, the conceptual barriers become somewhat less intimidating. Not eliminated, reduced. You remain far from a complete explanation. But the landscape of possibilities broadens. The cosmos begins looking less like a miraculous exception and more like a phenomenon that might arise naturally under appropriate conditions. That realization leads naturally toward another extraordinary idea. Perhaps our universe is not unique. Perhaps cosmic creation is not a singular event. Perhaps reality generates many universes, an enormous population, a vast collection, potentially with different properties, different histories, different physical conditions. The thought feels dizzying. For most of human history, people assumed Earth occupied the center of everything. Then Earth became one planet among several. Later, the Sun became one star among billions. The Milky Way became one galaxy among countless others. Again and again, humanity discovered that reality was larger than expected. The multiverse concept extends that trend dramatically. Maybe our entire observable universe is only one member of a much greater cosmic family. You are not yet ready to explore that possibility fully, but its outline is beginning to emerge. Certain versions of inflation appear to encourage it. Some quantum cosmological models accommodate it. Various theoretical frameworks seem surprisingly comfortable with vast populations of universes. Not all physicists agree. Many remain skeptical. Evidence remains limited. The discussions can become spirited. Academics occasionally express spirited disagreement using language so polite that outsiders might miss the argument entirely. A phrase like, "This interpretation faces certain challenges," can conceal enough intellectual firepower to power a small moon, yet the questions remain serious. If universes can arise naturally, could there be many of them? If there are many, what determines their properties? And what would that mean for the question of why this particular universe exists? The darkness around you grows deeper once more. The cosmic accounting books slowly close. Positive and negative energies settle into balance. The ledger remains intriguing, but beyond it lies an even larger horizon. A possibility stretching far beyond the observable cosmos. A possibility in which reality may contain countless universes, each with its own story, and somewhere among them, perhaps, drifts the one you call home. The horizon expands once again. Just when the universe seemed large enough to overwhelm comprehension, a new possibility arrives and casually suggests that your entire observable cosmos might be only one small part of something vastly greater. You drift through darkness filled not with stars, but with possibilities, the galaxies you know, the cosmic history you have traced, the billions of years stretching from the Big Bang to the present night. All of it may belong to a single universe among many. This idea is commonly known as the multiverse. Few concepts in modern cosmology inspire more fascination, skepticism, excitement, and occasional headaches, and understandably so. The scale involved is difficult to exaggerate. Imagine every galaxy in the observable universe. Then imagine that the entire observable universe is merely one region within a much larger reality. Then imagine many such universes, possibly infinitely many, possibly with different properties, possibly with different laws of physics. At this point, your imagination may be quietly filing a complaint. That is perfectly normal. The multiverse stretches human intuition to its limits. One mainstream historical fact is that several versions of inflationary cosmology, developed during the late 20th century, led some researchers to propose a phenomenon called eternal inflation. In these models, inflation does not necessarily end everywhere at once. Instead, some regions stop inflating and become universes, while other regions continue expanding. The process resembles a cosmic landscape, constantly generating new pockets of reality. You can picture bubbles forming in a vast sea. Each bubble becomes its own expanding universe. Inside one bubble, galaxies form. Inside another, perhaps different conditions prevail. The details depend upon the particular model. The imagery is imperfect, yet it captures the essential intuition. Reality may be far larger than the portion you can observe. In some versions of the multiverse, physical constants vary from one universe to another. The strength of forces, the masses of particles, the properties of space-time itself. Tiny differences could produce dramatically different outcomes. Some universes might expand too rapidly for galaxies to form. Others might collapse quickly. Still others could remain barren and simple. Many would be utterly unsuitable for complex structures, perhaps even lifeless. One quirky tidbit often discussed in multiverse conversations is that if enough universes exist, then somewhere there could theoretically be extraordinarily unlikely combinations of events. Popular descriptions sometimes run wild with this notion, imagining endless versions of reality containing every conceivable variation. The actual scientific proposals are usually much more specific and restrained than science fiction suggests. Still, the implications remain staggering. Because if countless universes exist, an old question acquires a new angle. Why does our universe possess conditions that allow stars, planets, chemistry, and life? For generations, people have marveled at how delicately certain physical parameters appear tuned. Small changes in some values could dramatically alter cosmic evolution. The multiverse offers one possible explanation. Perhaps many universes exist with many different properties. Naturally, observers find themselves in regions compatible with observation. After all, a universe incapable of producing observers will not contain anyone asking questions about it. This reasoning is often associated with what physicists call anthropic arguments. The idea remains controversial. Some researchers find it useful. Others remain dissatisfied. Many continue debating its explanatory power. Historians still argue whether anthropic reasoning represents a profound scientific insight or merely a temporary placeholder until deeper explanations emerge. the debate shows no sign of disappearing. As you drift among these possibilities, another challenge becomes apparent. Evidence, science ultimately depends upon observation, predictions, testing, verification. How do you test for other universes? That question lies at the heart of much criticisms directed toward multiverse theories. If other universes remain forever inaccessible, can their existence be scientifically confirmed? Different researchers answer differently. Some argue that multiverse scenarios emerge naturally from theories already motivated by observational evidence. Others insist that direct testability remains essential. The discussion continues, and it is one of the most interesting conversations in contemporary cosmology. You float between caution and wonder. The multiverse is not established fact, neither is it mere fantasy. It occupies a complicated territory where mathematics, observation, philosophy, and speculation intersect. That territory can be uncomfortable. It can also be remarkably productive. Scientific progress often begins by exploring possibilities before determining which survive confrontation with evidence. Meanwhile, the broader lesson remains valuable. The observable universe may not represent the full extent of reality. Humanity has encountered this lesson before, repeatedly. Ancient civilizations believed their local region encompassed most of existence. Later generations learned otherwise. The pattern repeated, again and again. Each time the cosmic stage grew larger, the multiverse may simply represent the next enlargement, or it may turn out to be mistaken. The future will decide. As your thoughts wander through this immense landscape, you notice something curious. The multiverse does not eliminate the original mystery, it merely relocates it. Suppose countless universes exist. Why does the larger system exist? Why does the mechanism generating universes exist? Why do the underlying laws exist? The old question returns, bought as ever. Why is there something rather than nothing? The multiverse may answer certain questions while leaving deeper ones untouched. Perhaps that is inevitable. Each explanation reveals new layers beneath it. Every solved mystery uncovers additional mysteries waiting below. The universe appears determined to remain interesting. And as you continue your journey, another profound issue emerges from the darkness: the concept of a beginning itself. You have spent much of this voyage tracing history backward, earlier times, smaller scales, hotter conditions, closer approaches to origins. But a subtle assumption has accompanied the entire exercise: the assumption that time itself possesses a meaningful before. What if that assumption fails? What if asking what happened before the beginning resembles asking what lies north of the North Pole? What if the concept of before ceases to function under sufficiently extreme conditions? The possibility sounds strange. Yet modern physics increasingly encourages exactly this kind of question. Ahead lies one of the deepest challenges in cosmology: not merely understanding the beginning, understanding whether a beginning, in the ordinary sense, existed at all. And the closer you approach that puzzle, the more mysterious time itself becomes. Time has behaved so reliably throughout your life that questioning it feels almost unreasonable. Morning becomes afternoon, afternoon becomes evening. A minute follows another minute. Yesterday slips behind you while tomorrow waits ahead. The flow seems obvious, natural, unavoidable. Yet as you continue approaching the deepest questions of cosmic origins, time itself begins acting strangely. The universe has a habit of doing that. Just when you feel comfortable with a concept, it gently removes the flaw beneath it. You have spent much of this journey rewinding cosmic history, galaxies shrinking, temperatures rising, distances collapsing. The process feels intuitive because every step assumes the existence of time. A before, an after, a sequence of events. But what happens when you approach the earliest conceivable moment? What happens when time itself becomes part of the puzzle? One mainstream historical fact is that Einstein's theory of general relativity, introduced in 1915, transformed humanity's understanding of time by revealing that it is woven together with space into a unified structure called space-time. Time is not a universal clock ticking identically everywhere. It can stretch, it can slow, it can behave differently depending upon gravity and motion. The revelation was extraordinary, and it remains one of the greatest achievements in scientific history. You can imagine space-time as a kind of cosmic fabric, not a literal fabric, of course. No giant celestial blanket floats through the universe. But the analogy helps. Matter and energy influence the geometry of space-time. The geometry influences motion. Everything interacts, everything participates, and crucially, time itself becomes part of the structure. This realization changes how cosmologists think about beginnings. Because if time is part of the universe, then asking what happened before the universe may be more complicated than it first appears. Consider the North Pole. You can travel north from London, continue northward, keep going. Eventually you reach the North Pole. Now ask a curious question. What lies farther north? The answer is not another location. The question itself stops functioning. North is defined in a way that makes the North Pole a boundary. There is no farther north. Some physicists have suggested that the beginning of cosmic time might resemble this situation. If time itself originates with the universe, then asking what happened before time may be like asking what lies north of the North Pole. The question assumes a framework that no longer applies. You pause to consider that. It is deeply counterintuitive. Your entire experience is built around temporal sequences, causes preceding effects, events following one another, stories unfolding. The possibility that time itself could have a beginning feels almost impossible to visualize. Fortunately, visualizing it is not required. Many correct scientific ideas resist intuition. The Earth circles the Sun, whether or not the motion feels obvious. Quantum mechanics functions, whether or not it seems sensible. Reality does not require permission from imagination. One quirky tidbit comes from popular discussions of time travel, where people often picture time as a river flowing steadily from past to future. Physicists, however, frequently describe space-time using mathematical structures that bear little resemblance to flowing rivers. The metaphor is useful, but reality appears considerably stranger. The closer you approach the beginning, the more those strange features emerge. Some cosmological models suggest that time itself may become increasingly ill-defined near the earliest moments. The distinction between past and future could blur. Ordinary temporal concepts may lose their meaning. The universe enters a regime where familiar language struggles to keep pace. As before, mathematics often advances farther than intuition. Certain proposals attempt to remove the singularity entirely. Instead of a sharp beginning, they describe a smooth transition. One influential idea emerged from work associated with Stephen Hawking and James Hartle. In simplified form, their no-boundary proposal suggested that the earliest universe might resemble a finite surface without an edge. The Earth provides a useful analogy. Its surface is finite. You can travel across it. Yet there is no edge where the world suddenly ends. Similarly, the earliest stages of the universe might avoid a conventional temporal boundary. The proposal remains subject to ongoing discussion and interpretation. Yet it beautifully illustrates how radically modern cosmology can rethink beginnings. Not every researcher accepts such models. Many alternative approaches exist. Some preserve a beginning, others replace it. Still others reinterpret it. Historians still argue whether future cosmology will ultimately describe the origin of time as a genuine beginning, a transition, or something even stranger that current language cannot adequately express. The uncertainty remains profound and fascinating. As you drift through these possibilities, you notice a recurring pattern. Each layer of explanation reveals deeper questions. The universe expands. Inflation occurs. Why? Quantum fluctuations exist. Why time begins why? The chain seems endless. Perhaps that is part of the lesson. Maybe reality does not contain a single final answer waiting at the bottom of the stack. Maybe explanations form an ever-deepening hierarchy. Or perhaps a fundamental principle remains hidden, waiting to be discovered. Nobody knows. The mystery endures. Yet uncertainty should not be mistaken for ignorance. Scientists have learned an extraordinary amount about the universe, the age of the cosmos, the evolution of galaxies, the abundance of elements, the properties of space-time. The evidence supporting modern cosmology is substantial. What remains uncertain are the deepest foundations, the earliest moments, the ultimate origins, the questions nearest the edge. And edges are where understanding often grows. As your thoughts continue drifting through the darkness, another possibility begins emerging. Suppose the universe did not begin from absolute nothingness. Suppose there was an earlier phase, a previous cosmos, a prior chapter, a state that existed before the hot Big Bang. The idea has appeared repeatedly throughout scientific history. Again and again, researchers have explored models in which cosmic history extends beyond the apparent beginning. Not a single origin, a cycle, a rebound, a transformation, the universe ending and beginning simultaneously, death becoming renewal, collapse becoming expansion. The thought feels ancient and modern at once. And somewhere ahead, among vast spans of time, entire universes may be preparing to rise from the ashes of earlier ones. The possibility unfolds slowly before you, not a single beginning. Not a lone cosmic spark emerging from eternal silence. Instead, a universe that participates in a larger rhythm, expansion followed by contraction, endings followed by beginnings. A cosmos that renews itself across spans of time so immense that billions of years become little more than passing seasons. The idea is surprisingly old. Long before modern cosmology existed, many cultures imagined reality moving through cycles. Worlds emerging, worlds fading, new worlds taking their place. The details varied enormously, but the intuition appeared again and again. Perhaps existence is not a one-time event. Perhaps it repeats. Modern science eventually developed its own versions of this possibility. Not because ancient myths proved correct, but because the mathematics of cosmology sometimes points towards cyclic behavior under certain conditions. One's mainstream historical fact is that throughout the 20th and 21st centuries, physicists explored various oscillating universe models in which cosmic expansion might eventually reverse, leading to contraction and potentially another phase of evolution. The details differ from model to model. The central idea remains remarkably consistent, a universe that does not simply begin once and end once. A universe with multiple chapters. You drift through one such possibility. Imagine the cosmos expanding for billions of years. Galaxies separating, stars aging, space stretching, eventually expansion slows. Gravity gains influence, the outward motion reverses. The universe begins contracting. Galaxies move closer. Temperatures rise, density increases. Everything heads toward an extraordinarily compressed state. Then comes the crucial question, what happens next? Older models often imagined a big crunch, the reverse of the Big Bang, a collapsing universe ending in extreme density and temperature. But later ideas introduced a more intriguing possibility. Instead of terminating completely, perhaps the collapse triggers a bounce, a transition, a new expansion phase, a rebirth. The universe falls inward only to emerge again. Not destroyed, transformed. You can picture a ball bouncing. The analogy is imperfect, yet useful. The downward motion becomes upward motion. The collapse becomes expansion. The end becomes a beginning. Some modern bounce models arise from attempts to incorporate quantum effects into cosmology. Near extremely high densities, quantum processes may alter the behavior predicted by classical gravity. Instead of allowing an infinite collapse, they may produce a rebound, a cosmic bounce, a new cycle. The mathematics remains an active area of research. No definitive answer has emerged, but the possibility remains captivating. One quirky tidbit is that certain cyclic cosmological models describe timespans so enormous that a single cycle could dwarf the entire age of the currently observable universe. Trying to visualize such durations is a bit like attempting to count every grain of sand on every beach, while simultaneously keeping track of every raindrop that has ever fallen. Eventually, the numbers stop feeling numerical and start feeling mythical. Yet cosmology routinely deals with scales that challenge imagination. That is part of its charm. As you continue drifting through these cycles, another variation appears. Not every model involves a complete collapse. Some proposals suggest that our universe may exist within a larger structure, where collisions between higher dimensional objects trigger repeated cosmic events. These ideas emerged partly from developments in string theory and related frameworks. The details become mathematically sophisticated rather quickly. Fortunately, the central intuition remains accessible. The Big Bang may have been a transition rather than an absolute beginning, a dramatic event embedded within a larger cosmic context. Historians still argue whether cyclic models will ultimately become central to cosmology, or remain valuable alternatives that illuminate specific theoretical possibilities. The evidence has not yet chosen a winner. For now, multiple scenarios remain under consideration, and that diversity of ideas reflects the complexity of the problem itself. Origins are difficult, perhaps the most difficult scientific problem imaginable. You are asking how reality came to be. Few questions demand more from human understanding, yet cyclic models offer something emotionally appealing. They replace absolute beginnings with continuity. The universe never emerges from complete nothingness. Instead, each phase grows from a previous one. Every ending becomes a seed. Every collapse becomes preparation. Every apparent conclusion hides another beginning. The pattern feels almost biological. A forest burns. New growth follows. Stars die. Their elements become ingredients for future stars and planets. Nature often recycles. Perhaps reality itself does too. Of course, elegance alone does not guarantee truth. The universe is under no obligation to behave poetically. Researchers must still confront observations, predictions, mathematical consistency. Theories survive only if they withstand scrutiny. Many beautiful ideas have failed that test. Many strange ideas have passed it. Reality remains stubbornly independent of aesthetic preference. As you contemplate these immense cycles, another realization emerges. Even if the universe repeats endlessly, a deeper mystery remains. Why does the cycle exist? Why do the laws governing it exist? Why does the larger framework exist? The old question returns once more, pomp-sealed, unwilling to disappear. Why is there something rather than nothing? The bounce delays the question. It does not eliminate it. Neither does eternal inflation. Neither does the multiverse. Again and again, explanations shift the mystery to deeper levels. Perhaps that is inevitable. Perhaps origins possess layers rather than a single solution. The farther you travel, the more the problem resembles a vast landscape rather than a single destination. And somewhere within that landscape, a new possibility begins to emerge. Maybe matter is not fundamental. Maybe energy is not fundamental. Maybe even space-time is not fundamental. Perhaps something deeper lies beneath them all. Something abstract, something surprisingly simple. Information paths, relationships, structures. An idea that would have sounded bizarre to most people throughout history. Yet increasingly, some researchers wonder whether information itself may occupy a privileged place in the architecture of reality. The universe may not merely contain information. It may, in some profound sense, be built from it. The thought drifts quietly into view. And as it does, the entire question of existence begins taking on an unexpectedly new form. The idea arrives gently, not with an explosion, not with a dramatic revelation, simply a quiet shift in perspective. For most of your life, reality has seemed composed of things: stars, planets, trees, people, atoms, particles, physical objects occupying physical space. The assumption feels natural because it works well in everyday experience. Yet modern physics has repeatedly shown that beneath familiar appearances lies a deeper level of description. And increasingly, some researchers have begun asking a provocative question. What if information is more fundamental than matter itself? At first, the proposal sounds abstract, perhaps even suspiciously philosophical. Then you begin noticing how often information already appears throughout physics. Particles possess measurable properties. Quantum states encode possibilities. Physical laws describe relationships. The universe seems filled with structured information, not merely objects. Pause. One mainstream historical fact is that mathematician and engineer Claude Shannon established the foundations of information theory in the mid-20th century, creating tools that transformed communications, computing, and eventually influenced discussions far beyond their original context. His work was not designed to explain cosmic origins, yet information theory would eventually find surprising connections to fundamental physics. You drift through those connections. A star contains information. A galaxy contains information. Even a simple atom possesses describable properties. The universe appears not merely as a collection of stuff, but as a vast arrangement of relationships and states. This realization became especially intriguing when physicists began studying black holes. Black holes, those famously mysterious regions where gravity becomes extraordinarily strong, raised a troubling question. What happens to information that falls inside? For decades, researchers debated the issue intensely. If information could be permanently destroyed, some cherished principles of physics might fail. If it survived somehow, understanding how became a major challenge. The resulting investigations produced profound insights. They suggested that information occupies a surprisingly central role in physical law. A quirky tidbit from black hole research is that one of the most famous scientific disagreements of the late 20th century involved wagers among physicists concerning whether information could truly disappear inside black holes. Few academic debates have generated so much intellectual effort around that sounds like a lost filing cabinet. Yet the stakes were enormous. The discussion touched the foundations of reality. As you continue floating through these ideas, another possibility emerges. Maybe spacetime itself is not fundamental. Maybe it arises from deeper informational relationships. This notion appears in several modern theoretical approaches. Different researchers formulate it differently. The details vary. The intuition remains similar. The geometry of space may emerge from underlying structures. The flow of time may emerge from deeper processes. Reality could resemble a grand pattern whose visible features arise from more fundamental informational rules. Imagine a digital photograph. Viewed normally, you see landscapes, mountains, clouds, and oceans. Zoom in far enough, and the image resolves into pixels. The larger picture emerges from simpler components. Some physicists wonder whether space-time might behave similarly. The world you experience could emerge from deeper informational ingredients. The idea remains speculative, yet it has attracted significant attention, partly because it offers new ways of thinking about old problems, including the problem of origins. If information lies near the foundation of reality, then perhaps existence does not begin with matter appearing in empty space. Perhaps it begins with the emergence of structure itself, pursues, relations, logical possibilities. The conversation starts sounding almost philosophical again. And indeed, the boundary between physics and philosophy becomes increasingly difficult to identify at these depths. Historians still argue whether future generations will regard information-based approaches as revolutionary breakthroughs or as useful frameworks that ultimately become absorbed into a broader theory. No consensus exists. The field remains active and evolving. Yet even without definitive answers, these ideas accomplish something important. They expand your imagination. They remind you that reality may not conform to the categories feel most familiar. Matter seemed fundamental. Then particles revealed deeper layers. Particles seemed fundamental. Then fields emerged. Fields seem fundamental today. Tomorrow may reveal something deeper still. Science often progresses by discovering that the foundations are not where people expected them to be. As your thoughts wander further, you begin noticing a recurring pattern throughout this entire journey. Every attempt to explain the universe relies on some kind of underlying framework: quantum fields, physical laws, mathematical structures, information, possibility itself. The mystery keeps retreating one step farther. Why do these frameworks exist? Why these laws rather than others? Why mathematics? Why information? The questions grow increasingly subtle. Yet they never quite disappear. Perhaps that persistence tells you something important. The search for origins may not resemble solving a crossword puzzle, where one final clue completes the grid. It may resemble exploring a coastline that continually reveals new inlets, coves, and horizons. Every answer expands the landscape. Every discovery uncovers additional territory. Far from being disappointing, this endless depth may be one of reality's most remarkable features. The universe appears understandable enough to investigate, mysterious enough to remain interesting, balanced perfectly between familiarity and wonder. And still, the deepest questions remain open. No final theory has arrived. No universally accepted explanation has emerged. The greatest minds in science continue debating, testing, calculating, imagining, matching. That search itself becomes part of the story. A story not merely about the universe, but about humanity's effort to understand it. Because as you approach the limits of explanation, another challenge comes into view. Not a challenge posed by the universe, a challenge posed by us, our instruments, our mathematics, our observations, our minds. The cosmos may possess answers that lie beyond current reach, perhaps beyond permanent reach. Ahead lies the frontier where human knowledge encounters its own boundaries, and there, at the edge of understanding, the mystery becomes deeper than ever. The edge arrives quietly. No warning signs appear. No cosmic fence marks the boundary. No enormous glowing arrow points toward a region labeled beyond human understanding. Instead, you simply notice that the questions have become increasingly difficult to answer. Not because people lack intelligence, not because scientists are careless, but because reality itself may contain limits that challenge every tool available to you. The universe is generous with mysteries. It is less generous with complete explanations. You float near the frontier where observation, mathematics, and imagination all begin encountering their own constraints. The experience is humbling and strangely beautiful. One mainstream historical fact is that astronomers can observe only the observable universe, a region limited by the finite speed of light and the age of cosmic expansion. Beyond that horizon may lie vastly more reality. But light from those regions has not had enough time to reach us. The concept sounds simple. Its implications are enormous. No matter how powerful future telescopes become, certain regions may remain permanently inaccessible, not hidden by technology, hid by the structure of space-time itself. Imagine standing on a shoreline during a foggy night. The ocean extends far beyond what you can see. You know additional water exists. You simply cannot observe it directly. Cosmologists often face similar situations. The observable universe is immense, yet it may represent only part of a larger reality. And if that larger reality influences cosmic origins, gathering direct evidence could prove extraordinarily difficult. Observation is not the only limitation. Mathematics presents its own challenges. Throughout history, mathematical frameworks have repeatedly revealed aspects of nature, long before direct observation confirmed them. The existence of certain particles, the behavior of gravity, the expansion of the universe. Again and again, equations guided discovery. Yet mathematics also generates possibilities that may be difficult, or even impossible, to test. Some theoretical landscapes become so vast that distinguishing among alternatives grows increasingly challenging. Researchers can write elegant equations describing countless potential realities. Determining which corresponds to nature is another matter entirely. A quirky tidbit sometimes mentioned in discussions of theoretical physics is that certain modern frameworks contain so many possible solutions that physicists occasionally compare the situation to searching for a specific grain of sand on a cosmic beach. The analogy may be dramatic, but it captures the feeling of navigating enormous mathematical possibilities. And still, the search continues, because difficulty is not the same as impossibility. Scientific history contains many examples of seemingly unreachable problems that eventually yielded to clever ideas and improved observations. No one should underestimate human curiosity. It has already carried your species remarkably far. You have measured distant galaxies, detected gravitational waves, observed planets orbiting other stars, mapped relic radiation left over from the early universe. The achievements are extraordinary. Yet the deepest origin questions remain stubborn, partly because they involve conditions unlike anything accessible today. The earliest moments of cosmic history occurred at energies vastly beyond current experimental capabilities. Particle accelerators can probe remarkable regimes. The newborn universe operated on scales even more extreme. As a result, researchers often rely on indirect evidence, observational clues, theoretical consistency, predictions that can be tested in limited ways. The approach works, but uncertainty inevitably remains. Historians still argue whether some questions about cosmic origins will ultimately become answerable through observation, or whether they belong to a category where empirical access remains permanently restricted. The distinction matters. Science depends upon evidence. Yet not every meaningful question guarantees an obtainable answer. That possibility can feel frustrating. You naturally want closure. A final explanation, a definitive solution. The universe appears less interested in providing those than you might prefer. Still, limits themselves can be informative. Consider the speed of light. It constrains what can be observed. Yet understanding that limit revealed profound truths about space-time. Similarly, recognizing the boundaries of knowledge can illuminate the structure of the problem. You begin noticing that every explanation rests upon assumptions. Every theory starts somewhere. Physical laws, mathematical frameworks, quantum principles, information structures. At some stage, foundations appear, and once foundations appear, new questions emerge. Why these foundations? Why not others? The chain continues, perhaps infinitely, perhaps not, nobody knows. This uncertainty has led some philosophers to suggest that ultimate explanations may possess an inherently different character from ordinary scientific explanations. Perhaps the origin of everything cannot be understood in the same way you understand the orbit of a planet or the formation of a cloud. Perhaps deeper principles are required. Others disagree strongly. They argue that apparent mysteries have repeatedly yielded to scientific investigation, and that cosmic origins should be no exception. The debate remains lively and productive because disagreement often drives progress. Questions sharpen, assumptions become visible, new ideas emerge. Meanwhile, you continue drifting through the darkness, not a hostile darkness, a peaceful one, a darkness filled with possibilities. The more you contemplate the limits of knowledge, the more remarkable knowledge itself begins to appear. Consider what humanity has already accomplished. A species evolving on a small planet, around an ordinary star, somehow learned to reconstruct billions of years of cosmic history. You identified galaxies, measured expansion, discovered quantum mechanics, detected ancient radiation from the early universe. The achievement borders on miraculous, and yet the mystery persists. Perhaps that combination is exactly what makes science so compelling. Understanding grows. Wonder remains, neither eliminates the other. As the edge of knowledge stretches before you, one final landscape begins appearing beyond it. Not a landscape of observations, not a landscape of equations. A landscape of debates, questions that refuse to settle, arguments that continue generation after generation. Scientists disagreeing with scientists, philosophers disagreeing with philosophers, physicists occasionally disagreeing with everyone. The search for origins has produced many ideas. No universal consensus. Ahead lies the gathering place of those enduring disagreements. The questions that refuse to end, the mysteries that continue inviting exploration. And perhaps, hidden somewhere among them, a clue waiting patiently for future minds to discover. The questions gather around you like distant stars, not isolated points, constellations of disagreement, entire galaxies of debate. The deeper you travel into the mystery of cosmic origins, the more apparent it becomes that intelligent people can examine the same evidence and arrive at different conclusions. This is not a flaw in science. It is often how science progresses. Ideas compete, predictions are tested, evidence accumulates, some theories strengthen, others fade. The process can take decades, sometimes centuries. And when the topic involves the origin of everything, patience becomes especially important. You drift through a landscape populated by competing explanations, inflation, quantum creation models, multiverse proposals, bounce cosmologies, information-based frameworks. Each offers valuable insights. Each leaves unanswered questions. Each attracts supporters and critics. One mainstream historical fact is that scientific revolutions have frequently involved intense debate before consensus emerged. The transition from Earth-centered models to heliocentric astronomy, for example, unfolded over generations rather than overnight. Cosmology follows a similar pattern. The biggest questions rarely surrender quickly. One enduring debate concerns inflation. Many cosmologists regard inflation as one of the most successful ideas in modern physics. Its predictions align impressively with observations of the cosmic microwave background. It helps explain large-scale uniformity. It provides mechanisms for generating primordial fluctuations, yet important uncertainties remain. What exactly caused inflation? What field drove it? How should it be incorporated into a deeper theory? The questions continue. Nearby, another debate unfolds, the multiverse. Some researchers view it as a natural consequence of certain inflationary scenarios and other theoretical frameworks. Others worry that the concept risks moving beyond empirical science if direct observational tests remain unavailable. Both sides raise serious points. Neither side has achieved a decisive victory. The conversation continues. Then comes the question of beginnings themselves. Did time truly start? Was there a bounce, a transition, a prior phase? Researchers explore all these possibilities. Evidence has not yet produced a universally accepted answer. The mystery remains open. A quirky tidbit about scientific debates is that many famous disagreements appear surprisingly polite when written down. Entire intellectual battles can hide behind phrases such as "this interpretation may face challenges," or "further clarification is desirable." To trained readers, these statements sometimes carry the energy of a medieval siege, conducted entirely through carefully edited journal articles. Human nature remains recognizable even inside advanced cosmology. As you drift among these disagreements, a deeper issue begins to emerge. What counts as an explanation? The question sounds simple. It is not. Suppose someone proposes a multiverse. Does that explain why our universe has its properties? Or does it merely shift the question to a larger framework? Suppose someone proposes fundamental laws. Why those laws? Suppose someone proposes a quantum vacuum. Why does that vacuum exist? Again and again, explanations seem to generate new questions. Some philosophers argue that this process may never end. Others believe a final explanatory principle exists somewhere beneath all others. Historians still argue whether humanity's search for ultimate explanations reflects a discoverable feature of reality, or an enduring characteristic of human curiosity itself. The debate reaches far beyond cosmology. It touches philosophy, logic, and even the nature of understanding. You begin noticing something fascinating. The disagreements themselves reveal progress. A few thousand years ago, people lacked telescopes. They lacked modern mathematics. They lacked knowledge of galaxies, quantum mechanics, and cosmic expansion. Many of today's debates would have been impossible. The questions have become more sophisticated because knowledge has grown. Even uncertainty has evolved. That realization feels strangely reassuring. Not knowing everything is not evidence of failure. It is often evidence that the frontier has advanced. You have reached questions difficult enough to challenge humanity's best tools. That is an achievement, not a disappointment. As the discussions continue around you, another theme repeatedly appears: humility. The greatest cosmologists frequently acknowledge uncertainty. They propose theories. They defend evidence. They revise conclusions when necessary. Science advances not through certainty alone, but through a willingness to remain uncertain where evidence remains incomplete. That attitude may be one of its greatest strengths. Reality is allowed to surprise you again and again, and it often does. The Earth was not central. The Sun was not unique. The Milky Way was not the entire cosmos. Space was not static. Time was not absolute. Each discovery altered humanity's perspective. Future discoveries may do the same. Perhaps one of today's speculative ideas will become tomorrow's accepted framework. Perhaps an entirely new idea will emerge. History leaves both possibilities open. The universe still contains many secrets. You can almost feel them waiting beyond the horizon of current knowledge, silent, unrevealed. And yet, despite all the debates, one remarkable fact remains: the question survives. Why is there something rather than nothing? Every theory attempts to engage with it. Some address it directly. Others approach it indirectly. None has eliminated it completely. The mystery remains one of the deepest ever encountered, perhaps because it touches every aspect of existence simultaneously. Every star, every galaxy, every atom, every thought, every possibility, all included. As your journey through disagreement begins winding down, you notice something unexpected. The goal was never merely to find a final answer. The search itself has value, the exploration matters. The act of asking changes how you see reality. The night sky becomes richer. Existence becomes stranger. Ordinary experience becomes more precious. Because the more deeply you investigate cosmic origins, the more extraordinary simple existence begins to appear. A pillow, a breath, a star, a moment of awareness. None of it feels quite as ordinary as before. And now only one stage remains. The debates recede. The equations grow quiet. The vast theories fade into the background. Soon you will return to the present night, to the universe that actually surrounds you, still mysterious, still beautiful, still here. And together, you will sit with the question one final time, not to solve it, but to appreciate the wonder it leaves behind. You return slowly, not because the universe has become smaller, not because the mystery has been solved, but because, after traveling through quantum fluctuations, inflation, bouncing cosmologies, multiverses, and the strange architecture of space-time, your attention gradually settles once more upon the simple fact that you are here, tonight, on a small world, orbiting an ordinary star inside a galaxy among billions. Inside a universe whose existence remains one of the deepest puzzles ever encountered, the question still waits quietly. Why is there something rather than nothing? You have followed it across enormous distances. You have traced cosmic history backward toward its earliest known moments. You have watched time itself become uncertain. You have explored proposals in which universes emerge from quantum processes. You have wandered through landscapes containing countless possible realities, and yet the mystery remains, not unchanged, richer, more textured, more fascinating than when you began. One mainstream historical fact is that modern cosmology has succeeded in reconstructing much of the universe's history from a fraction of a second after the Big Bang onward, creating one of the most successful scientific narratives ever assembled. That achievement alone is extraordinary. A species that evolved on a small rocky planet learned to measure ancient radiation, map distant galaxies, and calculate events occurring billions of years ago. When viewed from the proper angle, that accomplishment feels almost as astonishing as the universe itself. You pause beside that thought. Humanity often focuses on what remains unknown, and there is certainly plenty of that. Yet consider how far understanding has already traveled. Ancient observers looked upward and saw mysterious lights. Today, you know those lights are stars. You know stars manufacture heavier elements. You know those elements become planets. You know some of those planets may host life. You know the observable universe spans unimaginable distances. Knowledge has expanded enormously. Wonder has expanded with it. A quirky tidbit worth remembering is that every atom heavier than hydrogen inside your body was forged in ancient stars long before Earth existed. The calcium in your bones, the iron in your blood, the oxygen you breathe. All part of a story billions of years older than human civilization. You are not separate from cosmic history. You are one of its recent chapters. The realization feels comforting and slightly humbling, mostly humbling. The universe has been busy for a very long time. As you sit with that perspective, another thought emerges. Perhaps the ultimate value of the question is not that it demands an answer. Perhaps it invites a certain way of seeing, a way of noticing existence. The fact that reality exists at all, the fact that anything happens, the fact that there are stars, oceans, memories, music, mountains, mathematics, laughter, curiosity, and quiet nights beneath the sky, none of it was guaranteed. Or perhaps all of it was inevitable. You still do not know. Neither does anyone else. Historians still argue whether future generations will eventually discover a complete explanation for cosmic origins, or whether the deepest questions will always retain an element of mystery. For now, the future remains unwritten. The search continues. New observations will arrive. New theories will emerge. New minds will explore the puzzle. The conversation will continue long after tonight. And that is perfectly all right, because mysteries are not merely obstacles. Sometimes they are invitations to investigate, to imagine, to remain curious, to look upward and wonder. The universe seems particularly good at inspiring that response. Even after centuries of discovery, it still manages to surprise. It still hides secrets. It still stretches beyond the horizon of understanding. And perhaps that is exactly as it should be. You drift now towards stillness. The vast structures of cosmology begin fading into the distance. The equations grow quieter, the debates soften. The immense machinery of galaxies and quantum fields recedes into the background. Only the night remains, and your place within it. The stars above are distant beyond comprehension, yet their light arrives gently, patiently, crossing years, centuries, sometimes millions of years before reaching waiting eyes. The universe does not hurry, neither do you. The question that began this journey remains suspended somewhere beyond the stars, not demanding an answer, simply existing, a reminder that reality is stranger than it appears, and more beautiful. The darkness around you feels calm now, not empty, never empty, filled with possibilities, filled with history, filled with the quiet persistence of existence itself. You let your thoughts loosen their grip. The need for certainty drifts away. The need for conclusions grows softer. You do not need to solve the universe tonight. You only need to rest inside it. The cosmos has carried its mystery for billions of years. It can carry it a little longer. And as the stars continue their silent journeys through the night, you allow yourself to become still, to become quiet, to simply be. The story continues. Whether or not you follow every detail, galaxies will keep turning, space will keep expanding, questions will keep waiting, and somewhere far beyond the reach of current understanding, the origin of everything remains one of the greatest mysteries ever known. Perhaps one day it will be solved, perhaps not. Either way, the wonder remains, and now, as the night deepens around you, it is time to let the journey fade gently into the darkness. The universe is vast, the mystery is vast, and you are here. That is enough. As your thoughts grow slower, allow the images of expanding galaxies and ancient starlight to drift softly across the horizon of your mind, becoming quieter and more distant with every passing moment. Let the questions relax their hold, not because they have been answered, but because they no longer need to be carried tonight. The cosmos continues its patient unfolding without urgency, without noise, without expectation. Imagine the night sky stretching endlessly overhead, calm and clear. The stars shine without effort. The galaxies move through space without concern. The ancient light that reaches you now began its journey long before human history, and yet it arrives gently, asking nothing from you except a moment of quiet attention. You rest on a small world wrapped in a thin layer of air, beneath a universe vast beyond measure. Around you, everything is in motion, the Earth turning, the planet orbiting, the galaxy drifting. Yet here, in this moment, there is stillness. Let the immense scales shrink away. Let the equations dissolve. Let the debates fall silent. There is only the soft rhythm of the night, only the steady comfort of being present. Perhaps the universe came from a quantum fluctuation, perhaps from a bounce, perhaps from something no human mind has yet imagined. Whatever the answer may be, it belongs to the same reality that carries you now, the same reality that formed the stars, the same reality that formed you. And as sleep begins to approach, you can leave the mystery where it has always been. Among the stars, waiting patiently, the cosmos remains. The night remains, and for now that gentle quiet wonder is enough. End of script. Sweet dream.